Hi everyone, so today we're going to discuss a beautiful concept, and that's called the generating functions. And more specifically, we're going to discuss the exponential generating function, right? Which is actually very interesting. Which is actually a very interesting sequence, and we're going to see how we can use this really nice technique of generating function in order to really solve certain recursions, right? Certain recurrence relations. So it's going to be a very interesting discussion, and let's just get right into it. This is the problem number 1 from the Greece team selection test in the year 2016. And in this video, we're going to talk about the exponential generating functions and recursions. So how we can use this concept of generating functions in order to solve certain given recursions. Then we have the Taylor and Maclaurin series for e raised to power x, which is just a really standard representation. I'll just write it down over here as well. Well, e raised to power x is simply nothing but the summation from n is equal to 0 to infinity of x raised to power n divided by n factorial. I'll talk a little bit more about this in the question as well. And this is actually the Maclaurin series. This is essentially the Taylor series centered about x equals to 0. Then we're also going to talk a little bit about power series expansion. Then obviously we have GCD and Wilson's theorem to finish off the question, right? And at the end we have book sessions for senior math Olympiads and of course a similar challenging problem.
This video is sponsored by Cheenta.com. Since 2010, Cheenta has trained thousands of students from all around the world in mathematical Olympiads, physics Olympiads, computer science and informatics Olympiads, ISI CMI entrances, and research projects for school and college students.
Okay, so what have they given to us? So define A0 is equal to 3, and then they've given us a recurrence relation, right? And then they've not just asked us to solve this recurrence relation. Like, okay, finding a closed form for an, finding a one-step recursion for an is like one thing. They've gone a step ahead, right? They have asked us to find all natural numbers m such that the GCD of m and an is 1. Or in other words, m is relatively prime with an. Quite fascinating, right? So it's not just solving that given recursion, it's actually going one step beyond that. But okay, let's maybe see how we can deal with this. Well, the first thing that you should be knowing is that generating functions can be used to solve recurrence relation, right? And the most common generating function is summation an x to the power n from n is equal to 0 to infinity. If I call that as ax, that ax is my generating function, and this is called as a polynomial generating function, right? This is called as a polynomial generating function. Similarly, summation from n is equal to 0 to infinity of an x to the power n divided by n factorial. If I call this as my generating function, ex, you can just represent it by whatever. It's essentially a polynomial. This is called as an exponential generating function, right? So this is a polynomial generating function, and this is an exponential generating function. Okay, and why is it called a polynomial generating function? Well, it's clear to see that this is a polynomial. If you just expand this out, the summation, it's clear to see this is a polynomial. But then why is this called an exponential generating function? It is so called an exponential generating function because if all the AIs are 1, so A1, A2, A3, all the way up to AI, all the way to AN, if all of these are 1, then you simply get summation from n is equal to 0 to infinity of x raised to the power n divided by n factorial, because an becomes 1, and that is e raised to the power x, right? So it's called the exponential generating function because if all the AIs become 1, this is simply the Maclaurin series for e raised to the power x, right? Which is an exponential function. So that is why this is something called as an exponential generating function, and this is its standard form that I've written over here. Now the main kind of goal is to figure it out do we use a polynomial generating function or do we use an exponential generating function? And one of the things that I see for in a recurrence is if you have something like an n plus 1 as the coefficient of an, then it's a good idea to use an exponential generating function, right? It's a pretty good idea to use an exponential generating function, and that's what we're going to do over here. So I'm going to define my exponential generating function ax as the summation from n is equal to 0 to infinity of an x to the power n divided by n factorial, standard exponential generating function, right? So ax will be nothing but summation from n is equal to 1 to infinity. So I basically remove the 0th term, an x to the power n divided by n factorial, but then I also need to add the 0th term because I subtracted. I need to add it obviously to maintain the equality. What is the 0th term? Just plug in n is equal to 0 over here, you'll get 3, and that's given in the question because a0 is 3. Okay, great. Now what I'm going to do is I'm going to re-index this. Now the summation, I'm going to re-index it such that I'm going to replace n with n plus 1. And when I do that re-indexing, I'll get ax is summation from n is equal to 0 to infinity. Over here, I'll get an plus 1, x is for n plus 1. So every n becomes n plus 1. And this becomes n plus 1 factorial plus 3. Now they've given us the recurrence for an plus 1. Well, an plus 1 is simply n plus 1 times an minus n. So if I just plug that in over here, I'll get ax is equal to 3 plus summation from n is equal to 0 to infinity of n plus 1 an minus n divided by n plus 1 factorial times x is power n plus 1. So you have this weird looking thing over here, and I can understand, generating functions, they're not necessarily the most classy or the most elegant of things, but they actually help us a lot, right? You need to deal with a little bit of summations here and there, but it's actually fairly easy. It's a fairly standard technique. So just bear with me a little bit over here. Now I can just split this up. So this becomes summation from n is equal to 0 to infinity of n plus 1 an divided by n plus 1 factorial times x is power n plus 1. And I'll get negative summation from n is equal to 0 to infinity of n divided by n plus 1 factorial x is power n plus 1. Okay, awesome. But n plus 1 divided by n plus 1 whole factorial is just n factorial, right? So ax just simply becomes 3 plus summation from n is equal to 0 to infinity of an divided by n factorial times x is power n plus 1 minus summation from n is equal to 0 to infinity, the other term remains the same, n divided by n plus 1 factorial x is power n plus 1. So we've achieved quite some interesting stuff over here. Now what I'm going to do is I'm just going to take an x common from here, and I'm just going to take it out of the sum, because the sum is dependent on n. It's not dependent on x. So I can take an x common, right? I can take an x out of the sum. And if I do that, I'll get summation from n is equal to 0 to infinity of an divided by n factorial times x is power n, which is basically a generating function. And then what I'm going to do over here is just I'm going to add 1 and subtract 1. So just to maybe demonstrate what I'm doing, I'm adding 1 and subtracting 1 over here. So when I do that, I'll get n plus 1 divided by n plus 1 whole factorial x is power n plus 1 with the negative sign, of course. And then the other thing will be positive, because negative is positive. Sum from n is equal to 0 to infinity. What will we get? We'll simply get 1 by n plus 1 factorial times x is power n plus 1. So really, let's just clean this up a little bit. This entire thing is obviously ax. So this ax becomes 3 plus x times ax, right? And over here, this is nothing but the negative sum from n is equal to 0 to infinity. Again, if I take an x common, it goes over here, and this just becomes x is power n divided by n factorial. But if you recognize this is what I mentioned in the beginning. This is the Taylor series for e raised power x. I can just replace this entire summation with e raised power x. Right? Okay, great. Plus what we had remaining, right? N is equal to 0 to infinity of this other stuff. X is power n plus 1 divided by n plus 1 whole factorial. So we cleaned it up quite a bit, right? From this complicated looking 3 summations, one after the another, now we just have one summation, right? Because we use a little bit of ideas of generating functions and the Taylor series to clean it up a little bit, make it a little bit more dealable, right? Now, again, I'm just gonna reindex this a little bit, this last summation, and I'm gonna replace n with n minus 1. So kind of reindexing this a bit. So ax is just 3 plus x times ax, of course, minus x e raised power x. And when I reindex this, I'll get the summation from n is equal to 1 to infinity. So this just becomes x is power n, and this just becomes, replacing all n with n minus 1, this just becomes n factorial. Okay, awesome. So this summation, if you actually look at it, this summation is almost like e raised power x. But do you notice a difference? There is n is equal to 1 over here. E raised power x actually starts with n is equal to 0. But we can make it seem like e raised power x. It's actually very simple. So we had this term, and I'm going to make it from n is equal to 0 to infinity of x is power n divided by n factorial. So what I essentially did is I added the 0th term. But if I added the 0th term, I also need to subtract the 0th term to maintain the equality. And the 0th term, just plug in n is equal to 0 and you'll easily see that this is 1. So ax, well, and this is obviously e raised power x, right? So ax becomes 3 minus 1, that is 2 plus x times ax minus x times e raised power x plus e raised power x. So if I take all the terms with ax on one side, ax becomes this times 1 minus x is equal to e raised power x times 1 minus x plus 2. And if I divide by 1 minus x on both sides, I get ax is equal to e raised power x plus 2 divided by 1 minus x. Wow. So after all of that calculations, after all of that dealing with so many summations, Taylor series, reindexing and whatnot, we've actually found a closed form for a generating function. Just imagine how beautiful this is. You started off with ax is equal to summation from n is equal to 0 to infinity of a n x is power n divided by n factorial. This is what you started off with. But using the things that they've given us in the question, using the recurrence that they've given us in the question, and using that idea of Taylor series, and this reindexing, you've actually found a closed form for ax, and that's just incredible. That's really incredible. Okay, now I'm gonna do a little bit of observation, and it's gonna involve power series. Now, for those of you who have read binomials, this may seem very obvious, but I'll just go over this. So 1 plus x square, all the way up to infinity. This is clearly 1 over 1 minus x, right? And that is that's essentially the sum of an infinite geometric progression, right? So if I ask you the summation from 1 plus x square all the way up to infinity, you will just say it's 1 over 1 minus x. But as we see many times in mathematics, you also need to remember the other way around, right? So 1 over 1 minus x is actually equal to 1 plus x square all the way up to infinity, right? So this is what we call as a power series. The expansion of 1 over 1 minus x is actually this geometric sequence, right? And it's clear to see that this works. So let me just write down my exponential generating function. So ax was obviously 2 over 1 minus x plus e raised power x, right? 2 over 1 minus x plus e raised power x. Okay, now I'm gonna use this concept of power series to expand out this 1 minus x. So this just becomes 2 times summation from n is equal to 0 to infinity of x is per n, because that just becomes 1 plus x square plus x cube all the way up to infinity. And again, e raised power x, I can just rewrite this in the form of its Taylor series. So this just becomes x raised power n divided by n factorial. This is quite awesome actually. Now I can shift this 2 inside the summation. A constant, you can shift it both inside and outside the summation, doesn't really matter. So I shifted 2 inside, I'm going to multiply by n factorial and divide by n factorial. Remains the same quantity, right? X raised power n plus summation from n is equal to 0 to infinity of x raised power n divided by n factorial. Now, observe certain things. X raised power n is common in both summations. N factorial in the denominator is also common in both summations. So I can take those things common. I can put it into just one summation. X raised power n divided by n factorial is common, right? So I can just put it into one summation. What is left? 2n factorial plus 1. So basically, ax is nothing but summation from n is equal to 0 to infinity of 2n factorial plus 1 divided by n factorial times x raised power n. But do you notice something? What was ax? It was summation from n is equal to 0 to infinity of an x raised power n divided by n factorial. So we just need to compare terms. X raised power n, x raised power n. N factorial in the denominator, n factorial in the denominator. So an becomes this. So an is actually 2 times n factorial plus 1. Do you realize what we've done over here? We've actually found a very nice closed form for an. And really, all of the weird things that we used to do with recurrence, we just avoided all of that, because we use this concept of generating functions. So generating functions is a really amazing idea that you can use to solve this reconciliation, these recursions. It's just amazing, right? So now we have essentially solved the given recursion. We now know a closed form for an as a one-step recursion, and we can just plug in values of n and calculate the values of an that correspond to them, right? But this is not the end of the question. Like I was referring to at the beginning, they went one step further, right? They went one step further. They just did not ask us to solve the recursion. They asked us to find. I'm just kind of phrasing the question. What we have to find, we need to find all m belong to natural numbers such that the GCD of m and an is 1. So we need to find this. This is our goal for all n greater than or equal to 0. This is the goal. We need to find m. We don't need to find the solution to the recursion. We've already done that. But now we need to find this m. So I observed something. An is always 2 times some number plus 1. So it's always an even number plus 1. So an is always odd, because an even number plus 1 is always odd. So an is very clearly always odd. But that implies that the GCD of 2 raised power k and an will always be 1 for all k greater than or equal to 0. Because 2 raised power k will always be even, right? And an is always odd. So an even quantity and odd quantity will always have GCD equal to 1. It's pretty clear to see. But isn't that structure similar to what they want us to find? We want to find the GCD of m and n is equal to 1. Here we get the GCD of 2 raised power k times n is equal to 1. So is it possible? I'm asking a question. Is it possible that m is equal to 2 raised power k? Question mark. Right? Is it possible that m is equal to 2 raised power k? It very well might be true. We need to find all m belong to natural numbers so that this condition holds. Is it possible that all such m are actually powers of 2? That's the question. And to kind of and that is actually the case. I'll just reveal the surprise. Indeed, it is that all m are actually 2 raised power k. And how do we prove that? Well, it's a pretty standard way to deal with this. I'll just make a claim. So claim is that if m is greater than or equal to 3 and odd, then that means that the GCD of m and an cannot be equal to 1. So this is my claim. And just to remind you, in the question, we want to find m so that GCD of m and an is equal to 1. So if this claim is true, then that means m cannot be greater than or equal to 3 and odd. That means that m has to be 2 raised power k. So if this claim is true, my hypothesis or my current hypothesis that m is equal to 2k is all such m will be true. So effectively, I just need to prove this claim, right? So m is greater than or equal to 3 and odd. So that implies that there is a prime p such that p divides m. And I'll just give you some basic example. For example, just consider the number 39. 39, so we have 3 dividing 39, 3 is a prime, right? 13 dividing 39, 13 is also prime. So m greater than or equal to 3, no matter what natural number m is greater than or equal to 3, there will always be a prime p such that p divides m. Right? Now we'll use something called as Wilson's theorem. And what is Wilson's theorem? Well, it's pretty clear. P minus 1 factorial is congruent to minus 1 modulo p. Okay, awesome. And p minus 1 factorial, I can actually write this as p minus 1, p minus 2 times p minus 3 factorial is congruent to minus 1 mod p. Well, if you just reduce this mod p, this becomes minus 1 mod p, this becomes minus 2 mod p, this remains p minus 3 factorial is congruent to negative 1 modulo p. So this just becomes 2 times p minus 3 factorial is congruent to negative 1 mod p. If I just take 1 to the other side, I'll get 2 times p minus 3 factorial plus 1 is congruent to 0 mod p. But do you recollect something? An was actually 2n factorial plus 1. So a sub p minus 3 is actually 2 times p minus 3 factorial plus 1. But essentially what we are seeing is that this is a p minus 3 is congruent to 0 modulo p. What does that mean? A p minus 3 leaves remainder to 0 when divided by p. So therefore p divides a p minus 3. So this prime p divides a p minus 3 and this prime p also divides m. Right? So p divides a p minus 3 and p divides m. Therefore, the GCD of AP minus 3 and m is not equal to 1 because we have this prime p that divides both quantities. So it's clear to see that the greatest common divisor is at least p, right? And it's clearly not equal to 1. So therefore, my claim is true that it is not equal to 1. Hence, m cannot be greater than or equal to 3 and odd, right? So therefore, m cannot be greater than or equal to 3 and odd. So therefore, the only thing that is left for m to be is m can only take the value 2 raised power k for all k greater than or equal to 0. We need to define m. We have found m, and that's the end of the question, right? So this is a really amazing question, and we had to employ this thing called generating functions, which are used a lot in combinatorics and algebra. You'll see them in a lot of places. But generating functions can actually be one of the best tools, in my opinion, to solve certain really nasty recursions, right? Really nasty recursive relations can easily be solved via generating functions. So hope you learned something from that. Okay, so we have certain book sessions for senior math Olympiads. I am a compendium, polynomials by Barbeo, elementary number theory by Sierpinski, graph theory by Harari, combinatorics by Brualdi, secrets and inequalities, and functional equations and how to solve them by Christopher G. Small. So I have a similar but challenging problem, and this is probably a little bit easier. That being said, you just need to solve this given recursion with an exponential generating function. Again, you have this n minus 1 as the coefficient, n minus 2 as the coefficient. It kind of gives you the hint that you need to use exponential generating function, right? So maybe try this out, and if you're able to do it, let me know. Until then, I'll see you in the next video. Thank you very much and bye-bye.
Cheenta programs are designed for students who are passionate about mathematics. And they are personalized with one-on-one training, individual evaluation, and remedial sessions. The reason Cheenta students are successful over the last 10 years because they are taught by mathematicians and real Olympiads from leading universities in India, United States, and Europe. Some of our students come back to teach at Cheenta from Oxford, Cambridge, Harvard, MIT, UCLA, ISI, CMI, IITs, TIFR, and IISc. For more information, visit cheenta.com.